right, so my apology for starting the class so late today. I lost track of time. I'll make sure this doesn't happen again. I would just want to remind you very quickly for some stuff, and then we'll do some recap, and then we continue with the review. So your lab number 1 solution has been released, and I will try to see how we go. We definitely will still end the class in time today. I will definitely cover some relation kind of stuff, the most tricky part, and then the next time, on Thursday, I'll cover the function stuff. But for today, if we got some, maybe 5 to 10 minutes or 5 minutes, I can highlight certain stuff on lab 1 solution, but we can still continue on Thursday, or you can ask me tomorrow in the lab session. I will be there in the first 20 minutes tomorrow, but if you still want to reach out to me, you can feel free to drop me an email. We can make an appointment. And for your lab number 2, it's going to be very relevant to what we're going to talk about today, which is about relation kind of stuff, right? So we're going to talk about it. All right, so what I will do is I'm going to, before I get there, let's now do a very quick recap about what we spoke about last time. And I think for the post-condition exercise, I really want to dive a little bit deeper very quickly, maybe about 10 minutes or so, just to let you know why we're doing that. It's a very useful way, useful application of the set theory. All right, so last time we spoke about basically the basic set definition, membership, just notation. You want to make sure you know how to do the corresponding stuff in Rodin. And of course, you can look at the Event B summary toolkit, the PDF I sent to you. You can always look it up to see how symbols should be written in Rodin. And we talk about relating set using subset and proper subset. Especially whenever you talk about equality between two sets, S1, S2. Always remember this is 1, and also number 2, S2 should be a subset of S1 as well, right? So like bidirectional. And we're going to use that in that post-condition exercise. And we got the basic exercises, nothing special. You can check your answer, very straightforward. And then this is the post-condition exercise we started, and I will have some new page over there in a moment, and then I can go over the solution with you. Just make sure you're okay. And then when you actually get to your written test number 1, I know it's still kind of far away after the reading week, but I think that this kind of question is also very important. I'll give you some more example questions to try, maybe a little bit later. Okay, but make sure you kind of digest at least the example that we talk about in class. I'll get to here a little bit later. We'll definitely get to this example, just to see how we can specify the different post-condition in different notations, either with or without set operators, number 1. Number 2, to be complete, you need 1 and 2, both of them. What's going to happen if you only got one of them? Why are they incomplete by themselves? That's something we're going to talk about today, okay, in a moment. And then we spoke about power set last time, and it's a very important starting point in order to define relations. And I can review very briefly today after that post-condition exercise. And then we spoke about this formula over here, right? And I will try to discuss this formula again, just to give you a little bit more insight into it, just to brush up your memory, maybe back in 2030, the probability course, okay? Okay, and then, so these are the 2 ways to really consider this particular formula. The result is really that you don't need to prove it, it's something that's given. You can either interpret this way here to say we want to get all the subsets of size 0, size 1, size 2, all the way to size maximum. And the number of ways to really collect all the sets will be just equal to 2 to the power of this cardinality of the maximum set. Because the way to think about it is, let's say this is the set where we want to create a power set. Think about for each member over here, we got a binary choice, either to include it or not to include it. That's why I was trying to enumerate these binary bits over here, right? Go all the way, so that's why I got 2 to the power of how many positions we have, or how many bits we have, right? So these 2 ways of interpreting the formula, you can choose either one, but I think you should really understand both. But am I going to ask you to prove them? No. Okay, you can take it for granted, okay? But you need to know how to use them. Okay, so any question about the what we covered last time? Okay, if no, why don't we dive further? Oh, there's one thing I want to just mention quickly, just before I forgot. If you go back to the class website, I want to show to you 2 things that are added there. Number one is the underneath your course syllabus, that's iClicker attendance. I think we should do it today to give you credits, right? Give you the bonus. We'll do that maybe either during the break or right before the end of the class. We'll do that. And then I think click on that, and then everything there is really nothing new. That's really what we did back in that week of the experimental attendance check. Another thing which I just added as new, I will try to maybe post the iPad notes unannotated, maybe each time before the class. So for those of you who may want to print it out, you want to load it to your iPad, you can feel free. I'll try to do this, and then you can feel free, optional. Hopefully that's useful to you, just to bring to your attention. And if I don't really send you any reminder like today, you can feel free to just refresh your browser to see there's a second file here. Normally, I will try to post it, hopefully half an hour before the class starts, the latest. Okay? I'll try my best. Okay, let's now go back to the lecture itself. I want to have a final say about this postcondition exercise over here. Let's now make it very explicit about what we are trying to achieve. We have basically a method here, all positive. It's going to take some input, a set. Also, it's going to return another output, also a set. That's what we have. You can think about the all positive method is going to transform from the input into output. For example, the input could be something like, let's say, -1, 2, 3, -7, and then 8. Let's say. That could be a set. And the output, what we expect to see, will be all positive, which will be 2, 3, and 8. Very straightforward. Okay? And now what we want to do is to say, upon the termination, upon this point, right at the termination of this point, we want to check something called the postcondition. And postcondition is simply a Boolean expression there. It's going to evaluate to either true or false. There's no middle way. And this is the definition, right? Postcondition. It checks to see if the output is somehow correct with respect to the input. For example, you can see the output here is 2, 3, and 8. It is correct with respect to the input here because it contains every positive number in the input, right? So that's a postcondition. And what does it really mean when the postcondition is incomplete? That's something maybe that's a bit lacking from the understanding from last time, okay? So now let's imagine this. Let's say we have, let's say this is your implementation. Right? You try to execute it, and then at the end of it, you try to check your postcondition. Okay? Let's say the postcondition is simply R1. All right? Now, a postcondition is said to be incomplete in the following sense. Let's say if my implementation itself is faulty, it contains certain bug. In this way, my postcondition should be able to signal an error to say, now the postcondition fails, so your implementation should be faulty. Now, if the implementation itself is faulty, the output is simply not right. But somehow the postcondition can still pass. There's something wrong with the postcondition. Okay? Now, let me make the annotation here. So R1 here will be incomplete if it evaluates to true despite the implementation being faulty. That's a very important definition. Possibly you didn't understand it. Maybe I didn't explain that well enough. But in each case, let's now try to understand that better this time. All right? And let me give you one example. I claim that these two postconditions should be put together to check stuff in order to be complete. Let's see what they are. Okay? Number one here, well, think about, let me just do a diagram again. Think about I can now divide this particular input set into two parts. all those that are exactly positive, and all those that are not positive, right? So now let me try to rearrange them a little bit. Let's say I can put 2 here, 3, 7, minus over here, right? I can arrange them into 2 subsets. Think about this subset over here are all those that are strictly larger than 0. That's really what the all positive is supposed to do. On the other hand, this part over here is not exactly what I want, but they're still part of the input. They are non-positive. Or I can say they are just not the case larger than 0. So they are basically less than or equal to 0. Right? So we can divide the input into this subset and this subset over here. The output itself should be exactly equal to this particular subset. Right? That's a postcondition for this exercise over here. So this set over here, the pink one, should be equal to the green one. That's what we want to express in the postcondition. And if you look through the notes from last time, the very first version of the postcondition we try to specify, we simply say, this set here is simply equal to this set over here. That's all good. Okay? But now, we try to say we want to use some set operator to express the equality. As we said before, if you know S and T are equal, if and only if S is a subset of T and T is a subset of S. You can think about here, this is more or less corresponding to R1, and this is more or less corresponding to R2. That's what we're doing. Okay? Let's now read it. You can think about this part here, the green one. Right? Are you convinced this set comprehension over here is corresponding to this subset here? Right? Because we're saying that all the members such that it's in the input, which can be each one of them, but further constrained, it should be larger than 0. And that should be a subset of the output. And conversely, output itself should be a subset of this subset, right, on the input. That's the complete postcondition. And now we got to think about why choosing only one of them in isolation is going to make it incomplete. So that's a follow-up question. But up to here, are we okay? Number 1, you want to understand what a postcondition is. Number 2, you want to understand what do we mean by a postcondition being incomplete. Number 3, for this particular case, what does it really mean when we say the 2 sets are equal using subset relation, bidirectional? It's necessary. Yes? Despite the implementation being faulty, contains some error, meaning that it is some error in computation, which I'll show to you. Okay? Good. Right, let's now answer these 2 questions one by one. I think that's your first exercise, so we can just go over the answer. The first one, Q1. Let's say I only got R1 as my entire postcondition, let's say. Why is it incomplete? Let's say this will be my entire postcondition. No R2. Entire postcondition. According to the definition I just gave to you over here, to show that this R1 alone, being the postcondition, is incomplete, you have to give me some kind of like input and output pair, such that it corresponds to some faulty implementation, but R1 is going to tell you that it is okay. That's kind of the witness that we need to find. For the first exercise, I can give you the answer. But for the second one, maybe you guys can try to see if you can start coming up with some nice answer. Okay, I'm going to give you a witness. How about this? I'll give you some witness over here. Let's say the input over here is, let's say we still got -1, -7, right? Let's say the same. -1, -7, and then 3, 2, and 8. The same input as before. But what about the output? Let me give you something here. the output over here is, what about just 3 and 2? And 8 and 10. Sorry, I'm just running out of space, but here I got 3, 2, 8, and 10. First of all, are you guys convinced that if I have an implementation that's going to take this particular input and then return to you this particular output, which will contain 3, 2, 8, and 10, it is a faulty implementation because it gives me something that's extra, 10. But is the post condition alone, R1, going to say okay? It is, because here the input is indeed a subset of the output. Right? Because I'm only asking for subset relation in one way. That's not complete. I ought to really ask subset relation for the other way. If I added R2 right now, it's going to check to see whether this one here is also a subset of all the positive number of that. It's not, because you can see the 10 here is actually the extra one. That's going to make it false. Okay? So now let me try to go a little bit further. So this, let's say this here. Hopefully that's a little bit better than last Thursday. But let's now go one more. Okay, let's now do this. Let me just repeat the input, output here. And we got input -1, -7, -1, -7, 3, 2, and 8. And let's say the output over here is going to be, let's say, 2, 3, 8, and 10. So we know that from here to here is faulty implementation. And then you got to convince yourself, this one here, R1 over here is going to be true. R2, evaluating on this, is going to be false. Agree? R1 over here is going to ask for all the positive number in the input, which would be this, this, and this. Is that a subset of the output? It is. 328, 328. No problem. But if you evaluate R2 over here, it's not going to be good, because this one here is not a subset of the positive number from input. So you really have to combine R1 and R2 together to make it complete. If only R1 alone, this will be your witness. Okay? So this will be the witness to show that R1 alone as the post condition is incomplete. Is incomplete. All right. Are we okay with this? Better, right? I hope. Question?
So, part one of the conditions is that X is a member of input, right?
Yep.
But 10 isn't really a member of the input set. So, like, should R1 just be enough?
No, R1 over here, it's a set comprehension, right? So R1 is saying that this particular set is going to include all those members that's both in the input and positive. So this is going to evaluate to basically 3, 2, and 8. And when you evaluate R1, you're asking whether 3, 2, 8 is a subset of the output, which is over here. It is. So that's true. That's exactly the point. So we're talking about faulty implementation. Now, I'm not showing any implementation detail, how we actually came up with this particular faulty implementation, but it generates some extra input. It generates something that doesn't even belong to the input. That's wrong. Mm-hmm. Does that kind of answer your question?
Yeah, it does. So we need it both ways.
Yeah, we need both ways. That's exactly right. So if we only got R1 alone as the post condition, this faulty condition can get away. All right? Now, maybe I can ask you quickly as a follow-up. What if R2 alone is the postcondition? I can tell you it's also incomplete. Can you give me some witness to show me that R2 alone is incomplete? Meaning that, give me a witness that's actually going to pass R2, but it may not pass R1, for example. Are you able to give me that? Okay, I saw some hands raised. How about I try with you first?
Just 213
213?
as output, and the input's the same.
Yep. Because over here it's saying the output should be a subset of all those positive numbers in the input. Just choose something that's not in the subset, right? 213, for example. Right, I'll write it down. Okay, so here it could be input just the same. Okay, I'll just copy that. 3, 2, and 8. And then I'll recap. Basically 2, 1, 3. So in this case, you can see this really stands out over here. Because even though this is a positive number, but it doesn't belong to the input set here. So it wouldn't satisfy this subset over here. Right? Good. All right, so let me recap about the whole process over here again, and then maybe I'll give you more example questions to try as we go a little bit closer to the written test. But, definitely study this and come up with more witnesses if you can. Whenever you're getting some method where we are going to get some input and output, right? In this case, there's simply just two sets. And what we want to do is we want to specify some complete postcondition. And sometimes we may not be able to specify in a single one. So we might just need to have two separate ones. And when they work together, it's going to make it complete. So what we want to figure out is, if we only got one postcondition alone, is it going to be complete enough? If it is not, you got to give me some witness to show, as I just explained. Okay, think about this example here. And I got one more for you. I just want to mention that quickly, and then similar exercise for you. Now, the only difference is, rather than using the subset relation, right? It's a very useful rewriting exercise to say, can you rewrite subset using for all exists implies? Yeah, go ahead. Okay. You mean like equal? Yes, indeed. So that's really the first version that we did. So I would say sometimes we may be restricted to say, now you want to kind of separate the two between rather than use equality, you want to use two separate postconditions to check. In which case, you cannot really use the single equal. So that's why we separate the two over here. Yeah. Depends on how the question asks. If the question doesn't give you any restriction, you can feel free to go with the simplest one, using equal. But if it says you have to use some set operator, in that case, you may have to use a subset bidirectional. Question? You mean this one here? Yeah, sure. So this one basically saying, in order to satisfy this, we just need to make sure output is a subset of the positive input, which will be 3, 2, and 8. Right? That's what we say. And now you can see that.
Where did the 1 come from? 2 and 3 makes sense. If the output was 2 and 3, then it is a subset of all the positive numbers.
I think
It could be a 1.
this could be maybe not the correct one. I was just confusing myself. What about this one here? Maybe that's why you guys were confused. How about, for example, this one here? Thank you. How about just 2 and 3? That'll make more sense, right? Because in this one here, again, it's all my fault. So here, if I look at this one here, you can see output is over here. It contains a proper subset of the input that's positive, 3, 2, and 8. So it's going to satisfy this one here, no problem. However, if you try to check the same input and output pair on R1, it's actually not going to pass, because now is the input that's positive, which would be 3, 2, and A, a subset of the output here? It's not. Apparently not, because 3, 2, A, is it a subset of 2, 3? No. So this one here is going to satisfy R2, but not R1. Satisfies R2, but not R1. So that's why this one here is also incomplete. I hope that clarified for you. Okay, awesome, thank you. All right, tricky, but I think that you definitely want to put some time thinking about it, and then that will be good. So I'm going to leave this for now, and then I'll give you more example to think about slightly later. And for this one here, just some rewriting. You basically just want to rewrite this one here and this one here using for all, or exist, or implies, right? That's something we also spoke about in the review, okay? I will just reveal the answer to show to you, okay? Just to save a little bit of time. Okay, basically, if you think about this one here, if this set here should be a subset of that, you're basically saying for every element in here, it should imply that's also in here. That's exactly what you will see, right? You can look at the solution and then try to make sense out of it. And the similar question here, why is R1 alone incomplete? You can give us the same witness pair. And also, why R2 alone is incomplete, you can also answer in a similar way. It's just that we are expressing the postcondition differently. Okay? And what about in the test, for example? In the test, depends on how I ask you to specify the postcondition. I might say you can only use set operator. I'll be a little bit more explicit in the test, so there will be no confusion about what operators you can use. But in this case, we're using subset operators. On the other hand, if I say you cannot use set operators, in that way, you can actually, so this will be without. That's a typo for me. In that case, you can use for all and also implies, right, etc. Two versions, but the answer for showing that they are incomplete would just be the same, because they are equivalent expressions, just using different operators. Okay. And let me move on a little bit just to talk about that power set formula very quickly, and then we can move on to something a little bit new. I want to talk about this formula here. That's how we calculate this power set last time, right? I just want to look at my cheat sheets to make sure I don't give you the wrong number. Just bear with me. There we go. Okay. Let's look at this formula one more time. And we're going to use it again today when we calculate relations. So if you recall this formula here, N, I. So what will be the specific usage for this formula for this course? Out of N given elements, how many ways are there to make a set, which means no ordering, to make a set of cardinality, cardinality I. Right, so here you can think about the N here is about how many elements we are given, and the I here is about what's the cardinality of the set you want to make out of N elements. Okay? That's basically the interpretation of the choose operator. And according to the formula, this is we can say this is equal to, okay? The one I gave to you last time was just the definition. N factorial divided by n minus I factorial times I factorial. That's really the definition for the formula. But let's see how we can interpret that formula. I would suggest before we do any interpretation, it's good to simplify this slightly. But before I do that, question. Sorry? Cardinality of, no, it's about the power set. That's another story. So here I'm just only talking about the choose operator only. I'm only talking about this choose operator. Yeah, that's only what I'm talking about. So what you were talking about, maybe 2 to the power something, another way of interpreting cardinality of the power set is different. Yeah. Yeah, so the choose operator. All right, how do we simplify this slightly? Can you somehow divide this up? You can, right? For example, let me give you one example and then we can generalize it. If I have, let's say, 10 choose 2. By definition, 10 factorial divided by 10 minus 2 factorial and 2 factorial. And how do I simplify this part over here? This one will just be 10 factorial divided by 8 factorial, 2 factorial, which will be 10 multiplied by 9 divided by 2 factorial. Right, you can see here, this is 10 times 9 is really the result over here. Okay? And this one here contains 2 terms, which is corresponding to exactly this number over here. That's something I just want to see the correspondence in the example. And let's look at the general formula over here. Okay? When you actually want to divide this one here, it's going to be something like this. By definition, n factorial is going to be n times n minus 1 times n minus 2 all the way to, I'll put a placeholder over here. And how many terms do we need over here in the numerator? It should be corresponding to I, right? So it will be I terms. Right? And then I'll give you some visualization, but I just want to make the formula complete for you. And this one here, you can verify yourself. It's going to be n minus I plus 1. You can try to convince yourself if I decrement from n all the way to this number here, I got exactly I terms. Okay? That's going to be divided by I factorial. And I would like to interpret this formula here for you. How do we interpret that? Okay. Let's now take a look at this. If I got, let's say, n elements here, that's given. N elements, that's given. Okay, so I got n over here. Somehow I want to choose I elements from there. I want to choose I elements from there and make it a set. Let's make some intermediate step over here. Rather than making a set, why don't we make a sequence where order matters? And then we can get rid of the duplicates by another step. So step number 1, we can make a sequence of size I. So think about sequence position 1, position 2, position 3, all the way to position I. Position 1, position 2, position 3, all the way to position I. I could start with 0, but it doesn't matter. Okay, we got I position here. Now, for the first position, how many possibilities do I have? N, because I got n element here. What about the second one? Do I still have n? Since my ultimate goal is to really make a set out of the given elements, I shouldn't repeat the selection. So now that I already chose 1 from the first position, the second position I should get 1 choice fewer. So that should be n minus 1. And then the third one, n minus 2, and etc. Right? We'll go that way. So this really corresponds to the numerator we have. How many ways to really make a sequence. But for every sequence we make, we have to also get rid of the duplicates. Eliminates duplicates. For example, let's say if I got the set over here, let's say it's A, B, C, D. And I want to say 4 choose 2. Let's say. How many ways are there? First of all, think about I want to make a sequence out of size 2. And then, so here I got 4 possibility. And then here, because I can be A, B, C, or D. And here I got another 3 possibility. Right? But now, all those 12 over here might contain some duplicate. For example, I may get AB, BA. I might get BC, CB, etc. That's why I have to divide it by how many positions do I have? 2. So 2 factorial is really to get rid of duplicates. So you may have seen the previous course, right? 2 duplicates. All right, again, so this is eliminates duplicates. Yeah, you can either try to understand the interpretation first. It might be a little bit easier and more convincing when you apply this formula. When we apply this in the context of calculating how many members are there in the a particular cardinality for the power set member, or when we calculate the relation, as we'll see. Okay. And then let's now move on. Okay. And the next one should be, we are going to go for relation pretty soon. Okay. How about we take attendance right now, and then we'll move on to this tuples and relation. Okay. Let's do that. Let me stop the record. The timer. I forgot. Sorry. I was a little bit worried, actually. Okay, good. After a power set, it's now, before we move on to relation, final concept, which is called set of tuples. How do we define the tuple? Let's go over a little bit slides, and then we'll do some exercise together. All right. You're basically given n sets. Set number 1, set number 2, all the way to set number n. Okay, all the sets. And somehow we want to calculate, I'm pretty sure you heard of it, it's called Cartesian product or cross products of the n, and each one of them is going to be n tuple. And then let's now see, this is definition, and we'll just see one example to see how to calculate it. And once we have defined the set of tuple and do some exercise, we are ready to see what a relation is. And then subsequently will be the relational operators. Let's take a look. Let's now take a look at this one specifically, and then we'll calculate it. Okay, so let me just see. Okay, good. So you're basically we are basically going to follow this particular notation here. And the operator we're using is cross product, just times over here. Right, we got different sets, 1, 2, all the way to n. And the number of sets you're given from 1 to n also correspond to each element, which is going to be 1, 2, all the way to n. We got n elements in each pair. If you recall the definition for set comprehension, this is called an n tuple. It's going to be a member of it's going to be a member in the resulting set. Each member in the resulting set is a n tuple. N could be 1, in which case only a single element. N could be 2, in which case it's a pair. Or it could be 3, it could be 4, etc. Yeah, this one here just a mathematical notation. You can take a look at that and convince yourself, but let's do one example to make sure we understand how to manipulate it. And then I'll show you another way to really enumerate it exhaustively, which might help too. Let's try to do that. So now we want to calculate this cross product here, right? So what we can do is think about this here is S1. And this one here is S2. And this one here is S3. All the three sets, right? And when we want to calculate this, we can say it's equal to, by definition, each member in the resulting cross product set is going to be an n tuple. And what's n? 1, 2, and 3. 3. Okay? So we're going to have E1, E2, and also E3. Such that, and I'm using set comprehension notation again, right? That's something you really want to get used to gradually. How do we constrain E1, E2, and E3? It should be that E1 should come from this set. E2 should come from this set. And E3 should come from this set. Right? Let's now write it down. E1 should be a member of AB. And E2 should be a member of 2, 4. And E3 should be a member of dollar and %. Right? That's a set comprehension notation by definition. And now how do we enumerate it? All right? You can definitely try your own way, but I will show you one way that you may want to consider using a tree. Okay? Think about we start from here. So we start from the root of the tree over here. And then since we got 1, 2, and 3. So we got 3 different levels. We got level number 1. I'll try to use a different line. We got level number 1. We got level number 2. And also we got a last level. Okay? For the first level, we ought to choose for A or B. Right? So here, we might choose either A or B. All right? And then, for the next one, we might choose the second one. We're going to be the second elements. E2, it can be either 2 or 4. So we ought to choose 2 or 4. 2 or 4. Right? Now, I'm pretty sure you know how to generalize this. Right? Let's just finish that. And the third one, we ought to choose from dollar or %. Dollar or %. Dollar or %. Sorry, I'm running out of space, but you see my point. Dollar or %. And here, dollar or %. And how many do we have? Basically, you can now see that at the top, at the bottom level. 1, 2, 3, 4, 5, 6, 7, 8. Not surprising, because if you try to do a cardinality check, 2 times 2 times 2 is going to be 8. Okay? So you shouldn't be too surprised if we got some property like this. If I got, for example, S1 cross product S2, cross product all the way to Sn. What should be its cardinality? It should be the multiplication of the individual cardinality, right? S1 multiply S2 multiply all the way to Sn. All right, that's a set aside. Now, how do you enumerate them? You can think about here, for example, A2 dollar should be one pair. That should be one tuple, right? So I can definitely put it there. I can definitely put A2 dollar. This will be one of them, right? This will be the ultimate set. I'm not going to do them all. You can try. Let me do one more. Let's say B2. Let's say B2 dollar. This will be another one, right? Just following the tree, basically. We got B2 and dollar. That's just another one. And dot, dot, dot. You got 8 of them. Okay? That's a basic, right? That's cross product. Any question about cross product? Hopefully that's straightforward. And once we know about cross product, we will be ready for relation. Okay? And that's something I'm hoping to at least cover, and then end the class in time, and I'll make sure I cover properly on Thursday in time. Okay, let's talk about relation. Okay, so relations. How do we construct a relation? Let's get some definition understood, and then, again, we'll go back to some example. A relation is a set of mappings, each being an ordered pair. So we're only talking about a special case for cross product in some way. Only 2 sets are given, S and T. Usually we say the source and maybe the destination or the target, S and T. Let's say we got 2 sets over here, 1, 2, 3, and AB. How do we somehow define the relation between these 2 sets, right? Yeah, we're going to have some ideas to be clarified gradually. But let me just start with this. Okay, let's now switch. Okay, let's now switch here. So we talk about relation. You have to always remember it's a set of pairs. A set of pairs. Or if you like, order pairs, because the order of the element does matter. As we'll see next time, Thursday, one will be domain, the other one will be range. Ordered pairs. All right. And then let's now have one example here. Let's say when we talk about, let's say, a relation on, let's say, 1, 2, 3, and AB. So here, 1, 2, 3 is S, and AB over here is the T. Let's start with this. I'll start by asking you a serious question to clarify what a relation is, right? Number 1. Is 1A a relation on, let me just refer to S and T rather than the actual sets. This is the first question. Yes or no? I heard yes, because you might think it's an ordered pair, right? Okay, 1A. Okay, I heard yes. Any other answer, or you just agree? Agree? Oh. Guys, be careful, because didn't I say here, it should be a set of ordered pairs. It should be a set. Is this a set? Not really. Be careful. Right? That's why I'm starting with something that's not a relation that can be commonly misunderstood. But that's okay. You'd rather make a mistake right now, not in the test. So this is no. Nope, because 1A is not a set. All right. Second question. Now let me give you a set. All right, I'm going to give you a set over here, and then how about this? Is a singleton set containing B2, the ordered pair only, is it a relation on S and T? You said no. Why did you think that's no? It's an ordered pair. It's a set of ordered pair. Yeah, it should be S to T, not T to S. That's why ordered pair is important, right? So this one here, hopefully you don't see that as too tricky. Also no. because you can see B here actually comes from the T. And 2 here comes from the S. So they are in the wrong order. Okay? The order is wrong. All right? And now let's do one more. And then we can move gradually to the next step. Okay, what about is 1A and then 3B a relation on S and T? How about this? It is a set, it's an order pair, and the order is actually right? Okay, so now this one should be good. 1 and 3 come from here. A and B come from here. So that should be yes. Okay, so now get a better feel about what a relation is. Yes? Yes, that's a good question here. The observation was, what if the second question here, if we say, is this set here containing B2 pair a relation on T and S? In that way, yes, it would be, because the order is right. But this order is wrong, right? Yes? You mean sorry, which one? This one here? The third one, okay, sure. You mean rather than this one here, you want to have 3B and then 1A? Is that what you meant? Yeah, it will still be a relation, it's fine. They will be considered equal relation because relation is simply a set of pairs. And for the set, the order doesn't really matter. Okay, so let me write it down. Interesting. So here, for example, I might say R1, relation number 1 is, let's say 1A and then 3B. I might have another relation over here that might be just switching the order of the order pair. So maybe 3B and then 1A. Right, you can see here, this is equal to this is equal to that, just in different order. That's okay, because by definition, it's simply a set. So we can say R1 equals R2. Okay. All right, so now we're going to summarize by 2 important questions. Let's say we're given S and T, right, in this particular order. Now, 2 questions to conclude this page. Given these 2 sets, what is the minimum relation on S and T? Also, what is the maximum relation on S and T? So one is about the minimum, the other one is about the maximum. Of course, both of them should be a set, right? By definition. The first one might be the easiest. How about you say the first one? Yeah, I agree. Just remember, empty set is a relation, funny enough. Even though, well, that's actually by definition, empty set is a set of pairs or set of anything. What about the maximum relation on S and T? What's the maximum? Basically, the maximum, you have to say, I want to get a maximum set that's going to contain all the possible order pairs drawn from S and T. Cartesian product, yes, exactly. All right. All right, once we understand the minimum and the maximum, we can now try to somehow enumerate relations. That's what we'll do. All right. Okay, of course, on this page, I would say ultimately, the most important conclusion is minimum, maximum, empty, and Cartesian product or cross product. Okay, I got about 4 minutes. I think, okay. Yeah, I'll definitely catch up on Thursday. Let me see what I can do for the 4 minutes here. I think there's one thing I could possibly do, just for lab number 1, solution highlight. I can highlight other things. Give me 4 minutes, I will make sure I end in time. I'll continue from this, and then we're not too far away from finishing the review. What I want to do is, I want to highlight one part of the lab number 1. Other parts I will try to go over as well on Thursday. All right, I want you to look at the invariance part and think about the two I'm now talking about. So we got invariance for the bank 0, okay? And here I also try to encode requirements number 8. Okay, you can go back to requirement number 8 on your lab 0 instruction, sorry, lab 1 instruction to see what it is about. But here it should be D larger than or equal to 0. Okay? Now, I want to get to the point right away. Now, if you try to invariance which correspond to requirements number 8 versus another one over here, invariant number 3, about the credit limits for every individual customer, right? Environment number 3. Now, do you think these two can work together well all the time? Invariant number 3 and invariant number 7. Let's try to dive a little bit deeper, right? That's the only thing I want to highlight. This one is saying the aggregates of all the balances should be larger than or equal to 0, according to this requirement number 8. Another one, E-description tells me that for every customer, they might be allowed to go down to minus C, right? Do you think these two are okay? Is it possible to have one true, but the other one actually false? Is it possible? That's my question to you. Anyone? Are these two contradictory? Contradictory in the sense that they may not be able to true simultaneously all the time. Yeah, you want to say something? Yeah.
Yeah, it's not possible. There is a situation where.
Tell me the situation where both of them cannot be true at the same time.
Let's just say there's a bank with one account, and I am minus 10 dollars.
Yeah, exactly, right? Or let's say even more general. Let's say I got all the accounts in my bank. They all go down to their minimum credit level, just negative. In that way, if you aggregate all the amount together, is it possible that it's larger than or equal to 0? Not really, right? Okay, let me write it down, and then we'll be done. Just give me 1 minute. So these two over here are contradictory. When all the account balances, let's say, get to minus C. It is not the case that D larger than or equal to 0. It's not possible, so they're contradictory. So this actually shows some value of formal tool like a rodent, because somehow if you actually got invariant being false, in that way, you just cannot really get through all the proof obligation. Right? So the formal tool can really somehow help you capture some contradiction in your requirements. So that will be the first thing I'd like to highlight about these two. And then I might go to other relational operators once we cover them on Thursday. All right, thank you so much. And then I will see you maybe in the lab session tomorrow. Okay?